Alright, section 2.3, writing a good definition. So we've talked about our conditional statements, being true, being false, some logic, our converses. Now, what we're going to talk about today is how to write a good definition. The first thing, we look at this picture. So we see this picture up here. It says flappers. These are some properties of flappers. Now, if you look at the picture, you notice that there's some curvy lines, and then an H have a dot in them. So what we can say about a flapper, some properties of a flapper, we can say that there's one point on the inside of the figure, and then we have two curvy lines outside, with a point at the end of each line. So each curvy line has that point, and there's a point on the inside. So now we can figure out writing a rule for finding a flapper. So we can see a flapper, now we can try to find it. So writing a rule for finding a flapper, we can say a flapper is a figure with one eye and two tails. So if we see a figure that has one eye and two tails, it's going to be a flapper. And then we can write our conditional statement, which is our if-then. Well, if a figure is a flapper, then it has one eye and two tails. If at any time you need to pause and write all the information down, just pause it and then catch up. So this is what a flapper is. So a flapper, if figure's a flapper, has one eye and two tails. Now we can compare flappers and not flappers. Well, these are not flappers. Well, is our conditional statement still valid after comparing it to not flappers? Yes, because when we look at these, they don't have one eye and two tails. So write the converse of our conditional. Well, the converse would be, if a figure has one eye and two tails, then it is a flapper. So if it has one eye and two tails, it's a flapper. None of these figures here have one eye and two tails. This has one eye, no tails. Two eyes, two tails, and just two tails. They're all not flappers. Now, if we look at the third group of figures, we can use our conditional and our converse to find the flappers. Well, we know that a flapper has to have, if it's a flapper, then it has one eye and two tails. Well, which ones have one eye and two tails? D, one eye and two tails, and E has one eye and two tails. This is two eyes, two tails. This is no eyes, tail, and these aren't tails. Now, writing our definitions. When we get this, we can write the conditional. It's called a definition. In order for something to be a definition, both the conditional and the converse must be true. So if the conditional and the converse are true, then we have a definition. The two true conditionals can be written combined into a compact form by joining the hypothesis and the conclusion. That's the if and the then. Instead, we're going to use this phrase called if and only if. Now this is called a biconditional. So this if and only if, it's called a biconditional. Now we have a little biconditional notation, which is a P. It's a double arrow with arrows on both sides. Arrows on both sides. P if and only if Q. Now examples of biconditionals. We're going to test these definitions by writing them in the forms requested. It says a person is a senior citizen if they are 55 years of age or older. Well, our conditional, if a person is a senior citizen, then they are 55 years of age or older. Well, the converse to that would be, if a person is 55 years of age or older, then they are a senior citizen. Or biconditional, a person is a senior citizen if and only if they are 55 years or older. And this is true. A person is a senior citizen if and only if they are 55 years or older. Alright, now I want you to try to answer these two questions. When you're done, pause it, answer the two questions. When you're done, start it over, and we'll go over the answers. Okay, so hopefully you have your answers here. First one says a right triangle is an angle that measures 90 degrees. The conditional statement should be, if it's a right triangle, then the angle measures 90 degrees. The converse of that, we flip the if and the then. If an angle measures 90 degrees, then it is a right angle. Or biconditional, an angle is a right angle if and only if it is 90 degrees. That is true. The next one, a diamond can cut glass. Are conditional. If an object is a diamond, then it can cut glass. Converse, if an object can cut glass, then it is a diamond. The biconditional, if an object is a diamond if and only if it can cut glass. That's false, because there's other things that can cut glass. So it's a false statement there. It's a false definition. And then when we look at the last ones, are conditional. If an angle is 130 degrees, then it is an obtuse angle. The converse, if an angle is obtuse, then it is 130 degrees. Or biconditional, if an angle is obtuse if and only if it is 130 degrees. That is false. It could be 120 degrees, 170 degrees. They make up obtuse angles also. And then we get to adjacent angles. Adjacent angles. An important concept in geometry is adjacent angles. By examining the figures in the first two boxes, you should be able to form an idea about what adjacent angles are and what they are not. So when you look at these, try to answer these 4 questions, pause it. When you got them answered, start it up again. Alright, so hopefully you have your answers, and let's continue to go. So what do the adjacent angles have in common? So what do you notice about all the adjacent angles? They have a common right and a common vertex. So they all have a common right and a common vertex. Can adjacent angles overlap? No, they cannot. So adjacent angles are angles in a plane that have their vertex and one side in common but have no interior points in common. So they have no other interior points in common. So when we look at this, use your definition to name all the adjacent angles in the figure. Well, the adjacent angles are angles 1 and 2, 3 and 4, and 4 and 5. So they are the adjacent angles. So this was our note on writing a good definition.